This is Chapter 5, Lesson 6. In this lesson, we're going to learn about the Fundamental Theorem of Algebra. And we will use the Fundamental Theorem to determine how many zeros or roots a polynomial equation will have. And we'll also use it to solve polynomial equations that have complex solutions. Here is the Fundamental Theorem of Algebra. It says if you have a polynomial whose degree is greater than or equal to 1, then if you set the polynomial equal to 0, then you will have exactly n roots. The roots could be real or they may be imaginary, so the roots will be called complex roots. Another way to state this is the degree of the polynomial will tell you how many solutions there are. So, for example, we have this polynomial. And the first thing we have to do, using the fundamental theorem of algebra, is we have to make the polynomial equal 0. So we're going to subtract the 13x squared, and we'll add the 10x. So now our polynomial equals 0. Since this is a degree greater than 1, in fact it's a degree 4, there should be 4 solutions to this polynomial. So to find these 4 solutions, one thing we can do is graph. Over here on the left we have a graph, and you see the graph goes down here, it goes below the screen, but it turns around, comes back, passes through this point, and then passes through this point, and passes through this point. And so these are the 4 roots of the equation. So it appears as though the roots are at x equals 1, 2, 3, 4, 5, negative 5. We have a root at 0. We have a root at 1 and another one at 2. So there are 4 zeros or roots. We can see them on the graph. So next what we do is we use synthetic division to prove that they are zeros. So first thing I'm going to do is factor out a GCF here. If I take out the x, that leaves me with x cubed plus 2x squared minus 13x plus 10 equals 0. Using the zero product property, I know that x equals 0 is a solution. So that's that solution right there. Okay, now I'm going to put out the coefficients on this remaining polynomial, the x cubed plus 2x squared minus 13x plus 10. And I will do synthetic division with the other 3 zeros. So I'm going to start with negative 5. So I drop down the 1. 1 times negative 5 is negative 5. Add the column. Multiply by negative 5. Add the column. Multiply by negative 5. Add the column. This tells me there's no remainder. And since there's no remainder, that means x equals negative 5 is a root or a solution or a 0, whatever you want to call it. So it turns out that this one works, and this one we found by factoring. So then we can take what's left here, x squared minus 3x plus 2, and we can factor that to find our remaining 2 solutions. So this will factor as x minus 2, x minus 1. So our solutions are x equals 2 and x equals 1, which was what we found on the graph. So you can look for your solutions on the graph, but then you have to prove they are solutions by a combination of factoring and synthetic division. Okay, here's another example. It's a 5th degree function. The function already equals 0, so I know there should be 5 complex roots or 5 complex solutions. 5 solutions in the complex plane. Looking at the graph here, I see that I have zeros at negative 2, positive 1, and positive 2. There should be 5 zeros though, and I only have 3. So what I'll do is I will divide the ones that I can see on the graph, and what remains then will tell me the remaining 2 solutions. So I'll put out the coefficients, 1, negative 3, 3, negative 4, and 4. And I'm going to divide by negative 2. So just doing the math here, multiplying gives me 6, adding is 3. Negative 6, negative 3, positive 6, 2, negative 4, 0. So it turns out negative 2 is definitely a root. And now I can take the coefficients that are here on the bottom and I can just divide into that group. I don't have to go to my original equation, and I'm going to divide off the next 0. So dividing by 1 this time. And that also comes out to 0, so that shows me that x equals 1 is a 0 or a root of this polynomial. Then I can divide by my last 0. Dividing by 2, I have 1, multiplying, and then adding. Multiplying, adding, multiplying, adding, and that turns out to be 0, so we have our third root. What remains down here is x squared plus 0x plus 1 equals 0. So solving that will tell me the last two roots. So if I subtract 1, I get negative 1. Taking the square root, I get plus or minus I. So I have 3 real roots that I can see on the graph, and I have 2 imaginary roots, which are the ones that do not appear on the graph. But there are 5 roots total, as we expected, because it's a 5th degree function. I'm going to stop this video here. Part 2 to this lesson will have 2 more examples of finding roots where some of them are complex. And that's it.